This ceramic disc is held in perfect hover, locked into position above a magnetic track. It remains completely stable, enveloped by liquid nitrogen fog. In classical physics, electrical current always encounters resistance. As electrons move through a conductor, they collide with the atomic structure, generating heat. Energy loss is the accepted tax on motion. The floating disk represents a radical defiance of those mechanics. It is levitating because the material has reached a state of absolute zero electrical resistance. In this state, a current can flow indefinitely through the material, without losing a single watt of power to heat. This macroscopic levitation forces us to look past classical physics and down to the quantum frontier for an explanation. This phenomenon was first observed in 1911 by Dutch physicist Heike Kamerlingh Onnes. After liquefying helium, Onnes used it to cool a sample of mercury to extreme temperatures, reaching a milestone of 4.2 Kelvin, roughly -269 degrees Celsius. As the mercury cooled, its electrical resistance didn't just decline. At the 4.2 Kelvin mark, it plummeted in a vertical drop to absolute zero. Onnes had observed a total phase transition. The mercury had entered a state of matter where friction no longer existed. For over 40 years, the precise mechanics of how this frictionless state was achieved remained unknown. Onnes proved a frictionless state of matter was a physical reality, shifting the scientific burden from if it was possible to how it functioned. To find the answer, we have to dive through the surface of the ceramic and into its microscopic interior. This 3D model represents the crystalline atomic lattice, composed of positively charged ions. Under normal conditions, electrons move through this lattice as solo particles. Classical resistance occurs when these solo electrons strike the atomic lattice. Each impact bleeds energy away as heat. In 1957, the BCS theory provided the mechanism for bypassing these collisions entirely. Authored by physicist John Bardeen, Leon Cooper, and John Robert Schrieffer. Their model starts with the supercooled lattice. At these extreme temperatures, the ions are stable and quiet. As an electron passes through the grid, its negative charge pulls the positive ions slightly toward it. This localized deformation is known as a phonon. By drawing these ions together, the electron creates a momentary wake of concentrated positive charge, altering the electrostatic environment for the next particle. Negatively charged electrons inherently repel one another. However, the concentrated positive charge of the phonon wake overrides this repulsion, pulling a second electron toward the first. These two particles bind into a stable quantum state called a Cooper pair. These pairs move through the material in a highly coordinated, synchronized wave. They navigate the lattice without striking the ions, avoiding the violent collisions that cause resistance in classical conductors. This collective, synchronized motion is a superfluid dance. Zero resistance is achieved by utilizing the lattice's own vibrations to bind electrons into a stable quantum state that glides with absolute zero friction. Moving from the internal flow of electrons back to the macroscopic edge of the material, we find the second defining trait of a superconductor. This diagram shows external magnetic field lines attempting to penetrate the material. Superconductivity is defined by perfect diamagnetism, known as the Meissner Effect. When cooled, it spontaneously generates internal surface currents to defend its interior. These currents create an opposing force that perfectly cancels out the external magnetic field, bending the lines cleanly around the object. This magnetic expulsion is what we saw earlier. The ceramic disc rejects the magnetic field of the track, forcing it to hover effortlessly. A true superconductor is defined by these two absolute pillars: zero internal resistance and perfect exterior magnetic expulsion. Pure metals have severe limitations when subjected to the heavy magnetic stress of modern industry. Elements like mercury or lead are type 1 superconductors. They possess a single critical field threshold. If the magnetic pressure becomes too high, their superconductivity abruptly collapses. Modern technology instead utilizes type 2 superconductors, which are generally complex ceramics and alloys. As the diagram shows, type 2 materials allow magnetic field lines to thread through them in localized tubes called vortices. By venting magnetic pressure through these vortices, Type II materials can withstand massive magnetic fields without the entire system collapsing. This ability to handle extreme magnetic stress makes Type II materials essential for our most advanced machines. They power the massive superconducting magnets used in MRI machines to generate high-resolution images of the human body. Maglev transit systems apply the Meissner Effect to eliminate rail friction, allowing trains to travel at immense speeds. And in the Large Hadron Collider, supercooled coils provide the massive forces needed to steer particles through a 27-kilometer ring. The primary engineering bottleneck for all these systems is the extreme cost and complexity of the liquid helium or nitrogen cooling required to maintain the state. The ultimate pursuit in this field is the discovery of a room-temperature superconductor. Removing the cooling requirement would allow us to eliminate the electricity currently lost to heat during long-distance transmission. Because a superconducting loop can circulate a current indefinitely with no decay, it provides a method for high-density energy storage. Finally, by stabilizing the quantum coherence of Cooper pairs at ambient temperatures, we can build the large-scale superconducting circuits required for quantum processors.